So this is part two of the epsilon-delta series, and hopefully you got something out of part one. We haven't actually done any epsilon-delta proofs yet, but we said we were going to start with the easier ones, which were examining functions that approach infinity as x approaches infinity, and hopefully you got the idea of what is required to be shown, what constitutes a proof that something approaches infinity as x approaches infinity. I'm going to use an example from the last video just to go over a principle real quick. We proved the last time that the limit as x approaches infinity of the function 1/2 x was equal to infinity by showing that for any value of m, let me see. By showing that for any value of m arbitrarily large, we can find an n such that 1/2 x will be greater than m whenever x is greater than n. And we found that in this case, we showed that if n is equal to 2 times m, then if x is greater than that, that implies that 1/2 x will be greater than m, thus completing the proof. Now I did just want to point out in showing this that this is not the only way to arrive at the answer. All right, the answer that we find out for n is not unique. We could find, once we find one particular value of n that works, in this case it was 2 times m, anything that's larger will suffice. So we just went through and proved this. We came upon this example by taking the thing that we wanted to prove and rearranging it, isolating the x, and winding up with x is greater than 2m. But you could just make a random guess, actually, and show that it's true. For example, what if we don't want to let n, so in this case we went with let n equal 2m. Anything that's larger will also satisfy the conditions. We could say, instead, we could have started from scratch and have said let n equal not 2m but 10m. Alright, and the challenge here is to show that letting n equal 10m will also lead us to a proof. So we say, okay, let m be given, and then say we're going to make the claim that this statement here is going to imply this. So what you would want to do is that what you would want to do would be say, okay, we're going to let x be greater than n, which is 10m. All right, equal. So then when you have x is greater than 10m, we could divide both sides by 10 and get 1/10 x is greater than m. And then, I guess, sort of by transitivity, you have 1/10 x. Well, 1/10 x is less than 1/2 x, right? Because a tenth is less than a half. And so, by this, we could just eliminate this middle part of the inequality here, and then it necessarily follows that 1/2 x must be greater than m, provided that 1/10 x is greater than m. Right? Like these imply each other. So there's the point of all this is that the value of m is not unique, and there's always more than one way to go to the answer. All right. Usually, one of the challenging aspects of this is trying to work with an m. With value of n that you didn't find yourself. All right, you could be supplied with something, and if you can show if it's actually true, then you should be able to show it. But it's not. Some students might freeze up by saying, "Well, I'm going to suppose that n is not 2m like we worked it out in the last time, but rather 10m," and they would get here, 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 and they would freeze up at this point because they wouldn't know what to do with it. But if you just stop and think about it a little bit, you say, "Oh, okay. Well, since this is smaller than the thing that I'm trying to show is big, I can just use transitivity and say, okay, 1/2 x has to be greater than m," and that completes the proof. So there's always more than one way of looking at this, and so there are multiple paths that you can take to arrive at the actual heart of the proof. What I have next is we're going to prove that the function y equals x squared plus x approaches infinity as x approaches infinity. So once again, we want to find an n such that x squared plus x will be greater than m, a given m, whenever x is greater than n. So find an n such that this implies this. Okay, well this is actually pretty easy because it's going to illustrate one of the central principles of these epsilon delta proofs. All right, and the principle is as such. If you want to show that something is large, which in this case is x squared plus x, if you want to show something is large, find something that's smaller than it that is also getting large. That smaller thing presumably is going to be something that's easier to algebraically manipulate. So check it out. If I want to show that x squared plus x is greater than m, the first thing I notice is that x squared plus x, provided everything is positive, x squared plus x is greater than just x by itself. So what this means is, if I can show a legitimate proof, if I can show that x by itself can be made larger than m, then it will naturally follow that x squared plus x will also be larger than m, and thus the proof will be complete. So the first thing I notice is that the thing that I want to show approaches infinity is actually larger than something that's very simple to work with. So that's what I'm going to do. I need to show that x is greater than m. So all I'm going to do is say, well, I'm just going to say let the value of n therefore be the number that I'm trying to beat. So if you say to make this larger than 10,000, I'm just going to say, well, okay, all x just has to be greater than 10,000, and watch how that goes. So if I let n equal m, then we have x will be greater than n, which equals m. And that naturally follows that, well, we can just chain an inequality on the end of this and say, well, it's also true that x squared plus x is greater than this. And we've thus chained the inequalities in a manner such that we happen to cross the answer, right? Just like that last time. Take the two things on the end, cut out that middle stuff, and the proof is complete. So if you let m be given, right, all that you got to do is let x be greater than that number, which means this, because it naturally follows that this is also true, right? Which then implies that the left-hand expression is greater than the right-hand expression is m, and then that completes the proof. So that's kind of an easy one because the thing that I was talking about was already big. Sometimes it's not so obvious though, as in the case with not x squared plus x, but x squared minus x. I want to show now. I want to prove that I want to show that the function y equals x squared minus x approaches infinity as x approaches infinity. Now it's not readily comparable to just x by itself. It's not obvious. So you got to find out a way to show that this expression can be made greater than m whenever x is greater than some value n. So how do you do that? You want to come up with, this is where you want to arrive. X squared minus x is greater than m somehow. Now in the other problems, we could directly compare this this function here, the function that we were trying to show. We could directly compare that to something that's smaller but already getting large, or in the case of the two problems that we did in the last video, we could just take this inequality, isolate the x, and then set n equal to whatever came out on the other side. Just to do a brief recap, when we wanted to show that 1/2 x could be made greater than m, so we just rearranged this and said, okay, x would have to be greater than 2m, and we let this expression equal n. Or in the case of, I think it was a square root. We wanted to show that radical x was greater than m. So we just rearranged this and said, okay, well, we'll just let x be greater than m squared, and then we let this be our value of n. Can't really do that here because you have two instances of the x's, and it's not obvious what you do. It's not easily solvable. But if you go back to that principle, try to find something that's smaller than this that you know is also approaching infinity. This is what makes this such a good example, is that it's really simple and it illustrates the principle very nicely. It shows that you got to get it out of your head that there's like one accepted path from start to finish in solving these, in improving these limits. All right, it depends much more on your ability to be creative and think about the expressions that you're dealing with, rather than, you know, there's a step A, B, C, and D. Only the basic structure is intact. You just have to show this, find a value of n that makes that so. Any way that you can get from A to B in that regard is going to be a legitimate form of reasoning. So you have to be creative with this. This will really ready you to to do mathematics of this type. So it's a good exercise. I actually recommend pausing the video right here and trying it yourself. Try to find a function now that is less than this, but is still approaching infinity, so that you can play this game where you chain the functions and by transitivity show that this is true. So if you're going to do it, pause the video now and come back in a few minutes after you have toyed around with it. But otherwise, I'm going to continue with this right now. So we want to show that this is greater than m. We need to find a value of n that makes this so. So what I'm going to do is, I'm just going to factor this. I just get curious and say, okay, well, it'll suffice if we can show that this is true, greater than m. And maybe you want to pause the video now, and maybe this will give you a hint if you just stare at this for a little while. There's something in here that's going to bring us to the answer. What I say to do is, if this is true, then this is going to be true. But this is an easy statement to prove. All I have to do is find something smaller than this and show that it can be made larger than m. And that's very easy, because x times x minus 1 is greater than x minus 1 times x minus 1, on account of x minus 1 being less than x. Alright? And the good part about this is this equals x minus 1 quantity squared. Which is good news, because now we have that 1x there. Right? So we can forget about all this other stuff. As long as I can show that this can be made greater than m, the problem is done. It just falls apart. So that's what I'm going to do. From here, I'm going to treat it like I treated it in the video, in the two problems from the last video. I'll ignore all the stuff up until here and pretend that the problem started here. So I would say, okay, I want to show that this is large. Square root both sides, x minus 1 is greater than the square root of m, and x is greater than the square root of m plus 1. And I'm going to say that this will be the value of n that I'm going to use. And my claim is that, I'll write it up here, if x is greater than n, which equals the square root of the number that we were challenged with, plus 1, that is going to be sufficient to prove this, or to show this, and hence prove that the limit is indeed infinity. So I'll start here. I'll say, so we'll say let m be given, and then we'll say all that we have to do is set n equal to that number. So we can make x greater than radical m plus 1, and then you just proceed to reverse these steps. So I subtract 1 from both sides. If this is true, it necessarily follows that this is true, radical m. And then if this is true, it necessarily follows that I can square both sides because everything is positive, and I'll get x minus 1 quantity squared must be greater than m. And I'm going to, oh, it looks like I'm running out of room here. So after that, I'm going to kind of move this down here. And if x minus 1 quantity squared can be shown to be greater than m, Well, this is less, since this is equal to, I'll write it all out, x minus 1 times x minus 1, x minus 1. Alright, since this equals this, but this is less than x times x minus 1, and since this is equal to x squared minus x, we're run out of room yet? Since this equals this, look down the chain of inequalities, and we have shown that that indeed can be made greater than m, thus completing the proof. So the challenge of this was, it was all in this step here. It was knowing that, it was seeing that this expression could be transformed into this, well, not really this, but it was really more, it was this step here. Noticing that you could compare this to something that's more, that lends itself to algebraic manipulation a little bit more easily, and that could be used to finish off the proof. So go through those steps again. There's the entire thing. I'll just kind of map out the reasoning here. This is what we wanted to show. So we come down here, that's equal. Then here's the comparison part. Solve for it. Set that equal to n. Let n be equal to that number. And then there you go. Just work it out from there. So this is a pretty powerful technique. Right? If you want to show something is big, find something that's smaller than it that is also getting big. And if it's easier to manipulate, no problem. This can be done for a variety of types of problems. Pretty much no matter how complicated it is, you can always find a way to play around with it and simplify it. The last example I'm going to do here is, suppose we want to show that we want to show that the limit as x approaches infinity of, let's go crazy, we'll say like 2x squared minus 10x minus 5 is infinity. Now, we know the answer in advance. We know it's going to rise, so it should be, the answer should come to us rather easily. But how do you do it? You have to play that same game. We want to show that 2x squared minus 10x minus 5 is greater than m for some value of n that we pick. So the challenge really becomes finding something that's sufficiently smaller than this, yet algebraically malleable, that it will still work. Right away, you notice that the 2 makes this thing large. So what I'm going to do is I'm going to start like a chain of inequalities here. We'll say 2x squared minus 10x minus 5. That's automatically going to be greater than just regular x squared minus 10x minus 5. Alright, so we're just kind of breaking it down here. And then if you sit here and play with this a little bit, you could say that this thing here is greater than x squared minus 10x minus x, provided that x is greater than 5. Now we're allowed to assume that because we're taking x to infinity. So let me just make a little side note here. Provided that x itself is greater than 5, then we're allowed to make this inequality here. Whereupon this, if I come back around, that equals x squared minus 11x. And from there, it's kind of looking like the one that we just did, right? This equals x times x minus 11, which itself is greater than x minus 11 times x minus 11. So x minus 11 quantity squared. So it suffices to show that if we can prove that this is greater than m, we'll be in good shape. And the whole thing just kind of falls into place just like that last one did. Square root both sides and then add 11, and we'll wind up with x is greater than the square root of m plus 11. And we'll take that to be our value of n. And once we start out with that, we'll say, okay, let m be given. Arbitrarily large number doesn't really matter. And we'll start off our proof by saying that, well, show that if x is greater than the square root of that number plus 11, watch, I'm not going to go through it, but all of these steps can be reversed. As long as this is true, If we set x to be greater than whatever this number is, then when we subtract 11 from both sides and square it, we'll wind up with this inequality. And from there, all the steps can be reversed, right? Less than, less than, less than. This is less than this is less than the thing that we wanted to show. So ultimately, we wind up with this being on the left and one instance of m being on the right, and thus the proof is complete. And that's how to do them if they get more complicated and if they have more than one x in them. You just have to play around with it. There's no one way of going about it. You have to get a little bit clever with the manipulations. And I suggest you could try this with your own problems. You can just make this stuff up, because if you know that you already know in advance what the answer is. It's just a trick of finding the right series of inequalities and being able to logically follow it to its conclusion. So I suggest making up a few of these. Make them higher powers of x. Go insane with it. You should always, get some practice in learning how to manipulate these expressions to make them do what you want them to do. And this will be it for the infinity ones. Next time we will follow up with limits that approach numbers, or functions that approach numbers, not infinity, as x approaches infinity. So we'll be talking about asymptotes.